Today in this video, we're going to be talking about inferences about two proportions, and we're just going to be looking at part A. What we're talking about here is when you got two population proportions, and in this case, we're talking about when they're independent from each other, trying to decide if they are the same or not. So hypothesis testing with two samples and trying to check whether they're the same or not. To lead off with, here's an example, the idea of do airbags save lives? So the idea would be, as far as proportions, is the ratio of people that, if there's a fatality, is the rate of fatalities the same in cars that have airbags as it is in cars that don't have airbags? Of course, the idea would be that airbags would save lives. If that's true, well, then the ratio should be less. Less with the idea that, yes, there could be some variation involved just from randomness along with it. So we're going to test this, to find out whether or not, basically, do airbags actually save lives. Now, here's the initial numbers right here. We've got occupant fatalities, 41 out of 11,541, which is 35%, and 52 out of 9,853, which is 52%, which it does seem like this is going to be less, but at the same time, with randomness, it needs to be checked out, it needs to be tested. And so this is the kind of thing we're talking about today. We've got two different percentages, two ratios, two proportions, and we're testing to see whether or not they are the same or not. Is the change significant enough to claim that they're actually different? The null, as we go through this section, is going to be the same the whole time. It's going to be that the two populations are in some way the same thing, or that they're equal to each other. So the null is going to contain the equality, which would be that the two populations are actually equal to each other. Some notation and vocabulary, and a little bit of this that I have in here, we're not going to use. The part that has to do with two pooled sample proportions. We're not going to be using that today. If you're doing the traditional method of hypothesis testing, of course, you'll need a test statistic. For that, this is the formula that you're going to use. So you're going to be finding the differences between the sample and the claim. And over here, we've got, of course, Q is going to be having to do with not, and of course, N is the sample size. We've done all these things before here, so I'm just giving that to you. Probably, if you're in my class, won't be using the traditional method anyways. Like I stated earlier, though, in this section, the null is going to be that the proportions are the same and contains the equality. And, of course, the alternative is going to be that they are not the same. It does not contain the equality. We assume that equal proportions in the two samples, but pool samples into the one big sample. Now, we're not doing pool samples. That's when I said part A we're leaving out. But I've got some stuff in here for when I do it later on. So there's how we would calculate the pooled proportion for later on. But for today, you don't need to worry about that. Q, again, is just the complement of P. So it's 1 minus that. There are requirements. We're talking about a binomial distribution. So the requirements are this, that the sample proportions are from two simple random samples that are independent. Again, we're not doing dependent today. That's a different topic. Second, for each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. Just a comment back to this about being independent. You've got to be careful here. If this was a dependent situation, where the one affects the other, there's a different test for that, and so we would have to use a different test. So that's why I'm just covering the independent today. So let's go back to this one here. Do they actually save lives? Okay, so again, here's your null. That contains the equality. The alternative is that the population of the first group, which is going to be this one in this case, is less than the second group. Well, as we go through this, you're going to be using on your Texas Instruments a two-proportion z-test. And again, if this was dependent, this would be different. We're doing independent, so it's a two-proportion z-test. And, of course, we want this to be pointing to the left because this is going to go with the alternative. Now, notice here you need the numbers. So 41 out of the 11,005, 41, 52 out of it. And another example I'm going to do in just a minute here, you don't have the number out of that. All you have is a percentage. In that case, to use the calculator, you're going to have to multiply to get the number in order to do that. So you'll need the numbers here, not just percentages, when you go to fill this in. And we go through and we run the hypothesis test. We get a p-value of 0.02 or 0.03 if you want to round, which is less than our alpha. And so at this point we can say that we can throw out the null and we can accept the alternative. So our conclusion, there is sufficient evidence to support the claim that the proportion of fatalities for occupants in cars with airbags is less than the proportion of those without airbags. And that's pretty much the way these go. Okay, when you're testing proportions with two samples, it's the two samples, two proportions z-test, and you'll need both sets of numbers in order to do that. Now, if you did these traditional, well then, of course, you would go back and you'd compare your critical value to your test statistic, and you'd make the same decision. Of course, you'd have the same conclusion that way, but I'm using the p-value method. All right, let's look at one where, like I told you, I'm going to be giving percentages instead of the numbers. So in this one, there was a study of 200 randomly selected adult females and 250 randomly selected adult males. Notice the sizes don't have to be the same. Internet users, 30% of the females and 38% of the males said that they plan to shop online at least once during the next month. At a significance level of 10%, an alpha of 10%, test the claim that there is a difference between the proportion of female and the proportion of male internet users who plan to shop online. Here again, the null has got the equality. Now, in this case, you could maybe infer a less than greater than, but I'm just going to do a two-tailed. I'm just going to say, well, I'm just going to say it's different because it doesn't really say more or less. It just says that they're different. Okay, so I'm going to use this as my alternative here. Now again, if you're going to go through and have one of these with percentages, when it comes time to put them in your calculator, you're going to have to first multiply and get what the numbers are. So for the 30% for the females, there's going to be 60. For the 38% males, it's going to be 95. Then again, it's back to two proportions z-test, and 60 out of 200, 95 out of 250, and in this case, we're going to have not equal to. And so we're going to then go ahead and get that one, and we've got a p-value of 0.076, which is less than 0.1. Now, again, if you wanted to use the traditional method, here's going to be there's our critical value, and there's our test statistic, and you'd end up with the same number. It's beyond it, so it's outside the rejection region, or excuse me, it's in the rejection region. So in this case, there is enough evidence to reject the null, so to support the claim that there is a difference between the proportion of female and the proportion of male internet users who plan to shop online. My main point of this one is if you're given percentages, you're going to have to do a little pre-work before you can enter stuff in. All right, I've got one here that I want you to try. And I've got numbers here for you. I've got the percentages are written there, but it has to do with the polio vaccine and whether or not the polio vaccine actually reduced the number that were getting polio. So in 1954, an experiment was conducted to test the effectiveness of the Salk vaccine as protection against the effects of polio. Approximately 200,000 children were injected with an ineffective saline solution. That was the placebo. 200,000 were injected with the vaccine. Of those that had been given the vaccine, 33 of the children developed polio. So it's 33 out of 200,000. Of those that had been given the placebo, 115 out of their 200,000 developed polio. I want you to go ahead and try this one. You can see the setup right there, and you can find your conclusions. So once you pause this and give it a try. All right, and what you end up with here is a p-value of 0, which is a pretty significant conclusion then. So there is sufficient evidence, so we can throw out the null. There's sufficient evidence to support the claim that there was a difference in the percentage of children affected with polio that had the vaccine and the number of children infected with polio that did not get the vaccine. So the vaccine was doing its job. It was effective. That would be your practical statement there. All right, there's a few problems for you to try. Please make sure you're checking your answers, make sure that everything's going the way you want it to, that you aren't goofing up your calculator, and that you're answering them in the correct format. Have a good day.